So, visible spectroscopy. What is visible spectroscopy and why is it important for us? Spectroscopy is a technique for studying how substances absorb light. Different compounds absorb different wavelengths, and the amount of they absorb helps determine their concentration. This method allows to measure concentrations in solutions, observe reactions, and analyze different substances. This experiment focused on measuring the absorption of various ink solutions, understand how color intensity relates to concentration. Visible spectroscopy has long been used to study chemical compounds non-invasively, helping identify materials compositions. Techniques like FORS and microspectrophlorimetry allows quick, accurate analysis of various samples, including the pigments, dyes, and other chemical substances. For the first part, the spectrometer was first set up by placing a container of water in the device and following the instructions on screen. For each of the 7 ink solutions, a clean container was filled with 3/4 full and placed in the spectrometer. The device then measured how much light each ink absorbed, recording the highest absorbance level and the exact wavelength. For the second part, 6 different concentrations of lime cordial were prepared. Each solution was placed in a container and measured for absorbance. The device saved each reading between measurements. The unknown lime cordial solution was also measured 3 times to determine its concentration. On this slide, there are some images which are showing us some bits of lab experiment. When results been received for first part of experiment, blue ink absorbed light at 628 nanometers, while green ink peaked at similar wavelengths, 629 nanometers, but absorbed less strongly. This shows that blue ink has more intense color. Orange and yellow inks absorbed at lower wavelengths, 484 and 417 nanometers, with orange color being stronger. These wavelengths what were received are typical for both these colors. Purple and red inks absorb light in similar areas, around 526 and 525 nanometers, with close absorbance values. Purple absorbs slightly more. Black ink has the highest absorbance at 398 nanometers, meaning it absorbed a lot of light across many wavelengths, which give it dark appearance. For the lime cordial part, the results show the clear pattern. As concentration of lime cordial increase, so does their absorption. This pattern remains constant across the data. At a 20% concentration, the absorption is 0.157, showing relatively low light absorption. As concentration rises to 40, the absorption increases to 0.268, and this pattern continues through the measurements, reaching 0.681 at 100% concentration. For the unknown sample, the absorption measurements for all 3 experiments are 0.643. When calculate the percentage and adding it on a graph, the concentration will be 94.42%, which fits well with the other values. For the calculation part, to determine the concentration of unknown sample, I had to compare its absorbance to that of the solution with 100% concentration. By settling up a proportion, we find that the unknown sample's concentration is approximately 94.42%, what perfectly fits on a graph's line. To conclude, this experiment has shown how visible spectroscopy can be used to study how different substances absorb light at specific wavelengths, helping to identify colors and measure concentration. In the first part, each ink color has demonstrated a unique absorption peak. For example, blue ink has absorbed light strongly at certain wavelengths, while black ink has shown the highest absorbance overall, giving it a darker appearance. In the second part, a clear relationship between the concentration of lime cordial and its absorbance has been observed. Higher concentrations have led to the higher absorbance. This pattern has allowed us to estimate the known sample's concentration as approximately 94%.